Arc length. What do we mean when we say arc length of a curve? Suppose we have a function y equals f of x defined on the interval from x equals a to x equals b. Think of this as a piece of string. If we hold this string at both ends and pull it tight, the length of that string would be the length of this curve. But how do we measure the length of something that is curved? Well, the way we do it is we divide up this interval from a to b into numerous subintervals. And then if we focus in on the ith interval right here, we can see that the distance between these 2 points would be the distance between the point pi minus 1 and pi. Let's keep in mind that the coordinates for pi minus 1 is going to be xi minus 1 and yi minus 1. And the coordinates for pi will be xi and yi. And so to find the distance between these 2 points, we'll call that pi minus 1 pi. That distance is given by the distance formula to be the square root of xi minus 1 quantity squared plus yi minus yi minus 1 quantity squared. But we know that the distance between xi and xi minus 1, we typically call that delta x. So we have delta x squared. And then the distance between yi and yi minus 1 is this little piece of the triangle here, and we're going to call that delta yi. Now the reason we call it delta yi is because depending on which piece you're looking at, the delta y's can change, but the delta x's are always the same. So we have delta yi quantity squared. Now let's focus in on simplifying this expression. We know from the mean value theorem that yi minus yi minus 1 is equal to f prime of xi star times xi minus 1. This is delta yi, and on the other side we have f prime of xi star times delta x. So delta yi quantity squared is going to be f prime of xi star quantity squared times delta x quantity squared. And we can substitute this expression into here. Now when we do that, we're going to get the square root of delta x squared plus f prime of xi star quantity squared times delta x quantity squared. This will allow us to factor out a delta x squared inside of the radical, leaving us with 1 plus f prime of xi star squared. Now we can separate this into 2 radicals. We have the square root of 1 plus f prime of xi star squared times the square root of delta x squared. But the square root of delta x squared is simply delta x. So we end up with 1 plus f prime of xi star squared multiplied by delta x. And that is how long the piece is from here to here. Now what we need to do is add up all such pieces. So the arc length is going to be approximately the sum, I equals 1 to n, of the square root of 1 plus f prime of xi star squared times delta x. And then the exact length will be the limit as n goes to infinity of this sum. And this we know to be the definition of a definite integral from a to b of the function in question. And this is the arc length formula. So just to summarize, to find the arc length of a function with respect to the x variable, if we assume that f prime is continuous on the interval from a to b, then the length of the curve y equals f of x from x equals a to x equals b is the integral from a to b of the square root of 1 plus the derivative of the function squared dx. Or if we use Leibniz notation, we can rewrite that as the integral from a to b of the square root of 1 plus dy dx squared and then dx. Let's go ahead and take a look at an example. Find the length of the arc of the semi-cubical parabola y squared equals x cubed between the points 1, 1 and 4, 8. Now don't worry about the name of the graph here. When you graph points on this curve, you will see that it has a piece of the graph up here and also a symmetrical piece of the graph down here. But we want to find the length of the curve from the point 1, 1 to the point 4, 8. So we are focusing in on this portion of the curve. So the first thing we need to do, if we're going to do this with respect to x, is realize that we're going to be integrating from x equals 1 to x equals 4. But then our curve is y squared equals x cubed. We need to have y as a function of x so that we can take its derivative. So the first thing we're going to do here is solve for y by taking the square root of both sides. When you do that, you get the absolute value of y is equal to the square root of x cubed. And you can write that as x to the 3/2 power. And then when you solve for y, you're going to get a plus or a minus in front of that function. Now, it makes sense that we have a positive and a negative. Again, the positive half is the half that's above the x-axis, and the negative half is the half that's below the x-axis. So for us, we are only focused in on the part that's above the x-axis. So if we want to write it in function notation, my function f of x is x to the 3/2 power. Now to find the arc length, we know the formula is the integral from a to b of the square root of 1 plus f prime of x squared dx. So first thing I need to do is find the derivative of this function. We use the power rule to do that. We get 3/2 x to the 1/2. And then let's go ahead and find what we get when we square that derivative. So squaring this derivative is going to be squaring the function 3/2 x to the 1/2. And that, of course, means that we need to square 3/2 and we need to square x to the 1/2. And this gives us 9/4 times x. And so the arc length of this particular function is going to be the integral from x equals 1 to x equals 4 of the square root of 1 plus 9/4 x dx. Now we just need to complete this problem by doing the integration. This requires a u substitution. We're going to let u equal 1 plus 9/4 x. du will be 9/4 times dx. And then to make this thing work, what we're going to do here is put a 9/4 in front of our dx, that is, we are multiplying by 9/4, and then we'll put a 4/9 on the outside of the integral to cancel that. Upon doing this, the integral becomes 4/9 integral of the square root of u times du. Now we just need to know what are our new limits. Well, when x is equal to 4, u is going to be 1 plus 9/4 times 4, and this is equal to 10. So this is our upper limit. And when x is equal to 1, u is going to be 1 plus 9/4 times 1. And this, of course, is 13/4. All right, so now let's go ahead and finish this problem. We need to find the antiderivative. So let's remember this is really 4/9 integral of u to the 1/2 du. And this is going to be 4/9 times u to the 3/2 divided by 3/2 from 13/4 to 10. Doing the math here, we have 4/9 times 2/3 times u to the 3/2. And this is equal to 8/27 multiplied by, now we just need to plug 10 and 13/4 in for u. So we get 10 to the 3/2 minus 13/4 to the 3/2. Now, this is the correct answer, but we should not leave the answer like this. We should go ahead and change it back into radical notation. So let's go ahead and focus in on 10 to the 3/2 power. Remember, this is just the square root of 10 cubed, and that's the square root of 1,000. And if you pull out 100, you get 10 radical 10. Now, 13/4 to the 3/2 is a little bit more work. We're going to have 13/4 cubed, and then the square root of that. Now, let me just write this as the square root of 13/4 squared times 13/4. The square root of 13/4 squared is 13/4. And then we have the square root of 13/4. And I can write this as 13 radical 13 over 4 radical 4. But radical 4 is 2, and so we can write this as 13 radical 13 over 4 times 2, which is 8. So in the end, we can say our answer is 8/27 times 10 radical 10 minus 13 radical 13 divided by 8. And if you choose to multiply this out, it gets a little bit nicer. We'll have 80 radical 10 over 27 minus, and then when you multiply here, the 8's are going to cancel, and we get 13 radical 13 over 27. And so I guess our final answer could be expressed as 80 radical 10 minus 13 radical 13, all divided by 27. And that certainly is a better looking answer than the one that we have here. Now we can also find arc length with respect to the y variable. To do it with respect to the y variable, your limits are going to be on the y-axis, and your function has to be a function of y. So it's the same formula, 1 plus the derivative of the function squared, square root of all that, and then take the integral. So the main thing is you have to think of a function of y. So if I want to find the length of the arc of the parabola y squared equals x from 0, 0 to 1, 1, let's first just remember that y squared is equal to x. It's just a sideways parabola looking like this. And we're going to find the length from 0, 0 to 1, 1. So we're looking at this length right here. So if I do that on the y-axis, our y limits are going to be 0 and 1. And then when I'm thinking of g of y, remember g of y is equal to x. So when we say x is equal to y squared is our g of y. So we get a little bit lucky here. If g of y is y squared, then g prime of y is simply 2y. And now to find the arc length, it's just going to be the integral from 0 to 1 of the square root of 1 plus g prime of y, which is 2y, quantity squared, dy. And this is the integral of the square root of 1 plus 4y squared dy. Now, how do we do this integral? Well, it turns out this is a trigonometric substitution. And actually, it's easier if you leave it in this format. I'm going to let 2y be equal to 1 times tangent of theta. And that means y is going to be 1/2 tangent of theta. And so dy would be 1/2 secant squared of theta d theta. Now if I plug all that in, the arc length becomes the integral of the square root of 1 plus tangent squared of theta times dy, which is 1/2 secant squared of theta d theta. Now our limits are going to change. If y is equal to 0 here, then 0 is equal to 1/2 tangent of theta. And this means that theta would have to be 0. And if y is equal to 1, then this means that 1 is equal to 1/2 tangent of theta, which is the same thing as saying tangent of theta equals 2, or theta is equal to the inverse tangent of 2. So our new limits are going to be 0 and inverse tangent of 2. Now let's go ahead and complete this. The square root of 1 plus tangent squared is the same as the square root of secant squared, which is secant. And so what we have here is secant right here multiplied by secant squared. That's secant cubed. And the limits are the same. And then we get a 1/2 on the outside from the 1/2 that you see here. Now we just have to integrate secant cubed. Now if you remember, we did this in a previous video lesson, so I'm just going to pull from that result. The integral of secant cubed is 1/2 secant x tangent x, in this case it's going to be secant theta tangent theta, plus 1/2 natural log of the absolute value of secant theta plus tangent of theta. And so if we multiply out the 1/2, we get 1/4 secant theta tangent theta plus 1/4 natural log of the absolute value of secant theta plus tangent of theta. And then we have to plug in our limits, which go from 0 to inverse tangent of 2. And this is going to get a little bit interesting. Let's just talk about plugging in 0. When you plug in 0, tangent of 0 is 0, and secant of 0 is 1. So when you plug in 0, this goes away, and when you plug in 0 here, you get 1 plus 0, which is 1. But then we're taking the natural log of 1, which is 0. So when you plug in 0, this is all going to go away. So we really only need to plug in inverse tangent of 2. But this gets really strange, because when you plug in inverse tangent of 2, you get secant of the inverse tangent of 2 times tangent of the inverse tangent of 2 plus 1/4 natural log of secant of the inverse tangent of 2 plus tangent of the inverse tangent of 2. And although you can say that tangent and inverse tangent cancel out here and you just get 2, what is the secant of the inverse tangent of 2? To do that, you really need to draw a picture of a triangle. So let's suppose we have a triangle that has some angle alpha, and the tangent of that angle is 2, meaning that the opposite and adjacent sides would be 2 and 1 respectively. We can show that the hypotenuse here is the square root of 5. And now the secant of that same angle would be the square root of 5 over 1, which is the square root of 5. So this value right here is the square root of 5. So we have 1/4 times the square root of 5 times 2 plus 1/4 times the natural log of the square root of 5 plus 2. And this is the square root of 5 over 2 plus 1/4 natural log of the square root of 5 plus 2. So you get some pretty strange numbers in the end, but the process is actually fairly straightforward. And that concludes this video lesson.